Okay, so the background image you see is a fractal. Okay, fractal in the sense it is a self-similar object. However, you zoom in, you will see similar patterns throughout. One natural example can be trees. Okay, trees, most likely fern. Okay, fern, and also like cauliflower. Like if you take a big cauliflower, take a small cauliflower out of it, zoom the cauliflower to an extent that it looks like a bigger cauliflower, and it is like a big cauliflower. Okay, so that is another kind of geometry, something outside of your class 5, 6, 7, using protected like geometrical box and all this. Okay, so this is known as a fractal geometry. It is a geometry used to like measure curved surfaces, okay, or natural objects. So if you see, all man-made objects are mostly like, as you can see, rectangles, squares, circles, and all this. But if you see the trees, the geometry are similar. One branch will be divided into two. Each of those branches will be getting divided into two, and so on. It continues, making it okay. So this is a motivation how you see so many realistic trees, so many realistic persons in video games. Video games, okay. So Project IG. How many of you played Project IG? Oh, yeah. So very addicting game. So there you see like even nowadays the games, you see that so many realistic structures like aeroplanes moving in, helicopter moving in, firing and all those things. It's so real. How they make it using computer graphics, of course. But the hidden mechanism to make those figures is fractal geometry. Okay, fractal geometry, you can use it for computer graphics. Okay, heavily used in computer vision, all those things. So I will spend in next class a few couple of minutes showing how this image you can generate 2 seconds using Python for a given function f of z equals to z cube minus 1. Okay, I will tell you what are the rules and you can generate this image. Okay, so right. So first we will be discussing about is it clear? So differentiation. So differentiation is a gateway. Okay, it's a differential equations. We'll cover in the next unit. Okay. So differentiation, as you know, it is a rate of change of something. Okay, isn't it? Okay. So first of all, like you will revisit some of the classical ideas of differentiation. Okay, where like in your class 12th or something. Okay. So we will consider like a differentiable function. The differentiable function. Why we are considering a differentiable function? Because we are taking a derivative. Okay. Not differentiable, there is no meaning to take the derivative. Therefore, we are considering a differentiable function. And a function is f of x depending on one variable x. And so if I say if it is differentiable, then you should ask me it is differentiable in which domain. Okay? It can't be differentiable on whole real line. Okay. So I am assuming that it is differentiable on. That means this is your real line. You have A, you have B. All continuum of points through here, A to B. Okay. And we know from our previous knowledge of calculus, f dash x, say I'm trying to evaluate at a point x naught. Okay, how it is defined? You can use like the limit definition, limit delta x tends to 0, f of x naught plus delta x minus f of x naught divided by delta x. So this is known as the the forward method, or it can be written as limit delta x tends to 0, f of x naught minus f of x naught minus delta x divided by delta x. So this is like a backward. Okay, why we are calling it forward and backward? So you can see, like for the forward method, I'm interested in fx at a point x naught. Okay. Now for the first definition, what I am using? I am using x naught plus delta x. Okay. That means you are going forward. Okay. And then you are differentiating, like then you are subtracting the original function f evaluated at x naught. Okay. So therefore it is known as forward. For the backward, what you are using x naught minus delta x. That means you are going backward. Similarly, we will have similar names ahead to find derivatives of functions motivated by these definitions. So the point is, we will be working on discrete data sets. Discrete data sets. What do you mean by discrete data sets? So discrete data sets in the sense that you have, instead of this, okay, you have just points. So that means the knowledge of the points is given to you. The value of the function at these x values is given to you. At one of these values of x, okay, which is completely different from the continuous domain, like the continuous definitions. Therefore, we need to learn, okay, these methods. Therefore, we are revisiting differentiation again, but in a different way. Okay, so these are known as these are known as grid points. So for simplicity, for the first half of the course or of this unit, I will assume that these grids are uniformly spaced. Okay, uniformly spaced. We'll make things easy at first, then we'll move to a bit complicated. Okay, what does it mean? Like I'm considering a uniform grid. Uniform grid means xi plus 1 minus xi is the same as xi minus xi minus 2. Agree? How to visualize this? So you should first ask me what is xi, what is xi plus 1, what is xi minus 2. Okay, so it is like this. This is your point xi in one of your grid points. It is one of the points in the grid. This will be xi minus 1. This will be I plus 1. Okay, yeah. So xi minus xi minus 1, this spacing is the same as this spacing. Okay, and it should be for any I. For any I. Note that if you take I equals to 2, I equal to 1, I equal to 2, then we are taking these first 3 points, isn't it? Just to check. So it can be, I can be anything spanning so that it can be taken for any points. So what I am saying is all these spacing are equal. Any spacing you take consecutive points, it will be the same. Okay. So maybe throughout the course I will use delta x or okay to denote that step size. Yeah. So right. So we will have another notation. So at x equals to xi, we will evaluate the function f. What it will be? F of xi, isn't it? Okay, it will be f of xi, and that I will denote for simplicity as f of I. Okay, this is just a notation. So this is just a notation. So f of I am defining. If I am defining something, I use not just equal to. I'm using this equals to f of x of I. There is this guy is saying that it is defined. Okay. Similarly, Can anyone say what is fi plus 1? Yeah. It, um, all right. So I'll spill the beans first. Okay, I'll spill the beans first, and then we'll see how it is being derived. Okay. So if you want to compute derivative, it's not just derivative. It's something known as a numerical derivative. Okay. So numerical derivative, we say like df by dx, but it is being evaluated at x equals to xi. Then we have a first definition is fi plus 1 minus f of I by delta x. Okay. So this is a which method? Forward method. Forward, and we are taking the difference. Okay. We are taking difference. So it is forward difference method. Okay. Uh, so it is known as forward difference method. And another method at hand. So, like you can use fi minus fi by delta x. This definition, this exact definition we saw in our just previous definition, isn't it? Like f of x naught minus f of x naught minus delta x by delta x. That is a backward difference. So this is known as a backward difference. Okay. There is another definition. Okay, so this will be that not much trivial. So you can have like fi plus 1 minus f of I minus 1 by 2 delta x. Okay. So if you're trying to evaluate the derivative at x equals to xi, okay, at x equals to xi, then you are what information we need? We need the information of the previous point, I minus 1, and we need the information of the further point I plus 1. Okay. So let me seal out the beans. The central difference will be the most accurate scheme if you want to find a derivative. Backward difference will have similar kind of errors. Okay. So these are the formulas like we will need if you want to compute some derivatives. Okay, we have three different methods: forward difference, backward difference, and central difference. And you can see that we just need the data of the function at the points which you already have. Okay. Function x value. So what is given to us? The what x data set and the function value at those x data set. Okay. Is it clear? Then we are asked that evaluate the derivative at one of the points. Okay. Then we just need, to solve the derivative, we just need the value of the function at those points. Based on the value of the function at those given points, we will compute the derivative. Okay. All right. So I'll just take a simple example. Okay. So consider like this is an example. Consider this function f of x equals to 2x cubed plus x. Okay. Can anyone tell me what is df by dx? just checking how many people. Okay. So it is 6x square plus 1. Okay, you know that. Suppose I want to find, suppose we are interested in finding df by dx, okay, at x equals to 0. Or we can write in another way, f dash 0. What will it be? How you are saying it to be 1? Yeah, so it is 6 times x square, x is given to x naught is given to 0. So it is 0 square plus 1. So it is 1. Now we will check. Now we will check using our forward and backward and central difference schemes what values we get. Okay. So yeah. So we know f of 0 is 1. Okay. Suppose, like, in order to construct this numerical method scheme, we need a grid first, and the grid we had assumed to be uniform. So let us take the uniform grid. Okay. Say like this is x equals to 0. Okay. And this is x equals to minus 0.1, and this is x equals to 0.1. Okay. So our step size delta x is equals to 0. Suppose you can take any step size. Okay, up to you. But we will see that how much smaller the step size you take, the more accurate the result it gets. But it's using Python soon. Okay. So can anyone say to me that what is f of minus 0.1? You know why? Function values at each of the forward data set and the backward point, right? So what is f of 0. minus 0.1 and where your scientific calculator will come into? Okay. Anyone? So for this class, you need like a scientific calculator. Only if you use the calculator at this instead of using calculator on a laptop, it will be more useful because you can't take laptop into lab exam. Okay. So use it. So I think you got this quantity, right? And same f of 0.1 you can get. Yes. Without even computing, you can tell it. Can you tell me why? If you just see f of x equals to minus of f of x. Yeah, even odd function. Remember? Okay. So next we will apply like the forward method. Okay, forward difference method. Okay. So what it will be? You know it is. You know the method, right? So f dash 0 is equals to forward. That means I need a point ahead of 0. That is, it should be f of 0.1 is there. So f of 0.1 minus f of 0 by, why I am doing 0.1? Okay. So what is f of 0.1? What is f of 0? What is this quantity? I also did it. Okay, so yeah, what quantity you get? 1.02. So note that analytically we got df by dx at x equals to 0 and 1. This is our analytical result. Okay. and this is our numerical result. You can see that there is some error. It is not that big error, but it's 1.02. So it is close to 1. Okay. So this is forward difference. Can we do backward difference? So using backward difference, what you will do? F dash of 0 equals to, you need a point on the left of 0, which will be the next grid, that is minus 0.1. So it should be, what's the definition? F of 0 minus 0.1, right? By delta x. And what is this? F of 0 is 0, minus f of minus 0.1 is minus of 0.12, that is like this. So we are getting similar, the same result, isn't it? Okay. Now the central difference method. So f dash 0 is equals to, so what shall we do here? From the definition, you need a forward point, that is our forward point is 0.1 minus of 0, that is f of minus 0.1. Okay, by 2 times 0.1. Okay, so this is like f of 0.1 will be, so f of 0.1 will be, can you tell me this quantity? F of 0.102 minus f of minus will be minus of minus, that is plus, divided by 2 times of 0.1. I think it's the same. Okay. Yeah, it's the same. So here, like, we are getting the same output, either like which method we consider. Okay. So I'll give you a task. Okay. The task is, you find a function. Okay. Maybe a different function, and apply this method, all the 3 methods, and see which one is good. Okay. Here we were lucky that all 3 are coming to be the same, but it won't be. Okay. In other examples, this is just one lucky example. Okay. So we already know, because I already told you, the central difference will be more accurate. Well, it's the more accurate method than forward difference or backward difference. Okay. But I will show that it is indeed the case. Okay. So in not, like, we saw that there is some error. Okay. There are some errors. Okay. Like, the derivative was 1, but sorry, had the derivative to be 1.02 in all the cases. That means we have some error quantity. Okay. We have some error. So how to quantify this error? Okay, this error will be more important. See, for numerical methods, there will be lot of different methods, lot of numerical methods for differentiation. But we have to choose the best method according to our use. Okay, therefore, it's good to learn all the methods, but appreciate the method which is less error and use it in your application. So all these things which we are doing by hand, that can be done using Python. Okay. So for now, you might not be getting an intuition as to why and how, like, Python can be used in this course, but you will see how it will be used. Most importantly, you need a for loop in this course. Okay, for loop. All right. So let us start with some errors. Okay, errors. So errors in forward difference. So yeah. So note that here I am showing that the h is the step size. Okay, we already know we have a uniform grid. So that means f of I plus 1 is equal to f of I plus 1, and xi plus 1 is xi plus h. H is your step size. Okay. Now this should ring some bells that we need some Taylor series expansion. Okay. So here we will have the Taylor series expansion. Anyone tell me? This is f of xi plus h f dash of x at I plus h square by 2 f double dash of xi plus so on. Okay, that is like, to be professional, we'll write h cube. Okay, order of h cube. So whatever terms you have, you represent that as order of h cube. Okay, this is a notation, big O notation. You might encounter in your course in data structures. Okay, big O and smaller notations. So, and this guy, like, if you see, in order to find f dash of xi, what we need to do, we need to ignore these terms, isn't it? We need to ignore these terms. Then you can see that f dash of xi on the right hand side can be written as f of I plus 1 minus f of I by h, isn't it? But there will be some other terms, that is the order of h cube terms. Okay. So, sorry, not the order of h cube, like there will be some errors. So those errors we are calling as a truncation error. Okay. Because we are truncating our series. We are truncating our Taylor series. And due to that truncation, error is coming out. Therefore, it is known as a truncation error. Okay. So we'll see. Yeah. Can you derive this quantity? Can you derive this? See, in order to do that, take this of fi plus 1 and divide by h. You know that you can you can divide by h. You can divide by h because h is not 0. Therefore, you can confidently divide by h. Okay. So therefore, fi plus 1 by h to fi by h plus f dash of xi plus h by 2 f double dash of xi, and there are some other terms like order of h square terms. Okay. Yeah. Yes. So now, like if I want dash of xi, what I have to do? I have to do I have to do fi plus 1 minus f of I by h, then minus h over 2 f double dash of xi minus order of h square, right? Is it clear? Clear? So you can see that this is our forward difference method formula, right? Isn't it? Of xi, the right side is the forward difference formula. Okay, but we were neglecting this quantity. What is that quantity now? It is order of h. Why it is order of h? Why it is not order of h square? The reason is h is a small quantity because it's a grid step size. It will be always less than 1. So h will always be greater than h square. Okay, and we have to take the order for the bigger quantity. Therefore, you are taking order of h and not h square. Here I have written order of h square, but there is a bigger quantity in the front. I have to respect and take that quantity because it is bigger than the other guy. So order of h. So therefore, your forward difference method, this order of h. So if your method, whatever method, numerical method you are having at your hand, if your method at the end has order of h to the power k, then it is kth order accurate. Okay. So in our case, forward difference, it is order of h. So you can say it first order accurate method. Okay. You got it, right? So this method is, so forward difference method is first order accurate. Okay. Okay. So yeah. So we'll see this error similarly for the case of backward and central difference also. Okay. So you can appreciate better which one is the Okay, so we just saw in just we just saw that forward difference is order of h. Okay, that means h to the power 1. So it is a first order scheme. Okay. Now we are interested in checking what is the order for backward. Finding the order of accuracy for backward difference is your task. Okay. Next class I will ask. I will write. So task, compute the for backward difference. Okay. Try to find. Next class I'll call randomly. Okay. So next we'll move to the central order scheme. Okay. The central difference. So what is the error in central difference? So you know that for central difference we have used what? So f dash I is equals to fi plus 1 minus f of I minus 1 by 2h, right? That means applying we need fi minus 1 and we need fi minus 1. Okay, so therefore fi plus 1, how you can write? That is f of I plus 1, right? That is f of xi plus the step size h, right? Now you can use your Taylor series. What is that? It will be f of xi, that point, plus h f dash xi plus h square over 2 f prime of f double prime of xi plus so on. All right. Yeah. Now I need fi minus 1. That is f of xi minus 1. That is f of xi xi minus h, right? Because it is a uniform grid. So xi plus h, you will go to xi plus 1. Xi minus h, you will go to xi minus 1. Okay. Now you can write it as a Taylor series, right? Now see that instead of plus h as above, you have minus h. So it will be f of xi minus h f dash of xi. It doesn't matter for h square. Okay. So it will be plus h square by 2 f double prime of xi, but it will matter for h cube. Okay. By 3 factorial f. Why this is working alone? So you can see it is f triple prime of xi. Okay. Plus so on. Okay. So can you judge something out of this? Can you use something to prove? Any ideas? So we have to take the difference, right? It's simple. So what you have to do? You have to take fi plus 1 minus I minus 1. Okay. What you get? You get See, when you subtract f cancels, okay, then it will be 2h f dash of xi plus what is there? Plus f square, right? Oh, that gets cancelled. That's get cancelled. So it will be order of h cube, I think, right? So how we will get our f dash of xi? We have to divide by 2h. We need to eliminate that front coefficient of f dash of xi. So that means dividing by 2h, we get fi plus 1 by 2h, okay, equals to f dash of xi, okay, plus you can take the order of h cube on the left, okay. So what will happen? It will be order of h square. Is it clear? No, it won't be h cube because you are dividing by 2h. So it will be h square, okay. So now you can see that central difference scheme is all, it has the accuracy of order 2 because it is order of h square. Previously you had order of h. Previously you had order of h. Now you are having order of h square. That means which one is better? See, order of h square means which is bigger, order of h or order of h square? H, because h is smaller than 1. So when you square it, h square is less than h. Okay, so therefore in central order scheme, you are having order of h square. That means this is method is more efficient as compared to your first forward or backward method. Okay, so we have proved it that indeed it is the case. Okay, so yeah, so we concluded that central order method is a second order accurate scheme. Okay, it's a second order accurate scheme. Okay. Okay, so now I want to show like yeah, on the board you can see the function. Can you see the function? So like you have to compute the derivative of that function on the board. Okay, and it is a bit complicated looking function. Okay, it is a bit complicated. So it is your task to do in Python. Okay, so I have already done it here. So I have introduced like numpy as np matplotlib to plot. Okay, because I'll plot the actual function. I'll plot this function in Python. Okay. Then I'll take the derivative using forward finite difference, and I'll plot that derivative of the function. I will check whether analytically the derivative I have obtained, okay, by just hand calculation, how accurately it matches with the numerical found derivative. Okay, for 3 cases: forward difference, finite difference, and central difference. Okay, here I have only done for forward. I will leave it to you to do for central and backward. Got all the 3 in 3 different colors for the derivative over the analytical one. Okay, and then you can appreciate how which method approximates the derivative numerically and efficiently. Okay, so see, I have defined the function here like lambda x e to the power sine x cube by 4. Okay, you can see, yeah. Then I have defined the derivative f prime. That's the analytical derivative. Okay, that's the analytical derivative. So I can plot fp. I can plot fp. Okay, so it will be fp versus x. Okay, then you will get a curve. You will get a curve. Okay, here I have taken h to be 0.1. Here I have taken h to be 0.1. The purpose of this exercise is a bit different. What is the purpose of this exercise? See, throughout our examples, we fixed our step size. h equals to 0.1. I want to understand how the result is affected, how the error is affected. We saw like forward difference is order of h, first order. Error for backward difference is also order of h, that's a task. Error for central difference is order of h square. Okay. Now keeping that in mind, that doesn't give us an idea how the error is varying. Okay. If a function is given to you, okay, that we can only know by coding. Okay, that's where the computing comes into picture. The purpose of this exercise is I want to analyze this function, how the derivative, numerical derivative minus the analytical derivative, the quantity, that is the error, is changing if I change the step size h. Okay, understood? Yeah. So if you see, I have done this thing like increased h for every iteration, h is decreasing by 10, 0.1, then 0.1 by 10, 0.01, 0, then next iteration 0.01 by 10, 0.001, so on. Okay, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, minus 4, like that. Step size, I am decreasing the step size. Okay, then we will see error versus the step size, how it is. Okay, it is not the fact that if you decrease the step size, you will always get accurate results. This is the fact I want to show. Okay. So you can see I have done here what method? Anyone? See, FP1, I have done FP1. FP is your analytical derivative, right? FP is your analytical derivative on this line. Okay. Now FP1 is your forward difference scheme. That is, I want to compute the derivative at x equals to 1. I want to compute the derivative at x equals to 1. Okay. And I am using the forward difference method, f of 1 plus h minus f of 1 by h. Okay. Then what I am doing, I am storing the results in f approx. Okay. You will see f approx as a data set. Okay. What it is storing? It is storing the value of h, right? Then it is storing the forward difference numerical derivative fp1. Okay. Then it is storing the fp minus fp1, the error, the difference between the analytical derivative fp, okay, and the numerical derivative fp1, okay, the difference. All right. So then for each after this method, I am taking h equal to h by 10. So you understood, right? For every run, there will be a new value of h, and it will be h by 10, the previous by 10 of previous quantity. And for that, it will compute the forward difference again and find the error. Okay. Then I will plot the error versus the data of step size. Okay, how it looks. So don't worry about this print 0 colon 1.3e. That is like I am trying to take 3 decimal places after the decimal point. Then I have to give 0 colon 1.3e. Okay, you are saying to Python that I need 3 decimal places after the 3 decimal places after the decimal point. Okay, if you need 4, you can add 4, 1.4. Okay. So similarly like this, okay, since the error is going as possible as 10 to the minus 12, minus 13, I have taken 15 here. Okay. So then what I am doing, I am extracting the data. Okay. I am extracting the data here, f approx. Sorry, the first column, f approx colon comma 0. Okay. The first column. What is the first column? It's the data of step sizes, h. Okay. What's the second column? Sorry, third column. I should have written third column here, 0, 1, 2. The third column is the error. Okay, that is the error column, right? Yes. Any issues? So now if I plot first column versus the second column, I will get how the error is spreading or how error is varying with the variation of step size h. Okay. Okay, so this is the data you can see. Okay, h, then the approx derivative, then the approximate error. The error is going as high as low as 10 to the minus 9. Okay, somewhere it is 10 to the minus 1. Yeah, you can't predict how it is varying, right? So we need to plot it. data visualization. Okay, you need to plot it. So after you plot it, it looks something like this. Okay, it looks something like this. What does it say? So yeah, maybe. Yes. So as you can see, h is on the x-axis. Okay. See, when h is 10 to the minus 2, the error was high. Right? Can you see that? Now, as you decreased h towards left side, you see, as you slowly decrease h 10 to the minus 4, 10 to the minus 6, so on, then your error started decreasing. Error started decreasing, right? Then as you decreased more, then as you decreased more after 10 to the minus 8, okay, like 10 to the minus 10, 10 to the minus 9, it started increasing again. The error started increasing again. Now it is increasing. Now again it is increasing. How much you decrease the step size h, it is increasing. The error is increasing. Okay. So therefore, from this example, you can see for real that always decreasing the step size doesn't guarantee you that your error will be less. Always. Okay. It doesn't guarantee you. So yeah, it is okay till 10 to the minus 8, but after that it started to degrade. Okay. So this is just an example. I want you to do this for the other two methods. Okay, for the central and for the backward method. That is one programming exercise. Second exercise is you will plot the analytical derivative. So see, this function is differentiable. Now you can get f dash of x, right? Analytically. I think, yeah. Yes. Yeah. Can you get analytical derivative for this function? Okay, that's what I have written in FP, right? FP. So here is the, yeah, FP is your analytical derivative here. I have already defined. Okay. Yeah. So you can find the analytical derivative. Okay. This is your second task. Plot the analytical derivative. I have just written it as a function, but you have to plot it. FP of x versus x. So you know how the analytical derivative looks. Am I? Then on the top of it, in a different color, you plot the numerical derivative via the forward difference, backward difference, and central difference. Okay, you understood? These are the two tasks. One task you already know. Second task is this. Okay. So I have given you an outline of this example, how it looks, how it varies with h. Your example will be to do for backward difference and central difference. Second, how the derivative looks for analytical derivative. Second, for forward, backward, and central. Okay. Done. So next class, randomly, I'll ask. Make sure like this. Make sure like because this course doesn't have another lab component, so we have to consider both theory and lab simultaneously. Okay. You want the code? That's the first question. Okay, so after we found first order derivative f prime, df by dx, we will next go to double derivative. Okay, I will just skim through, but I will just show how we do it. Okay, so like the double derivative. Okay, right. You know the trick, isn't it? So if I tell you, can you find the double derivative numerically? I would say you already know the trick. Okay, how? You just simply find. So our aim is to find f double dash I, that is d2 f by dx2 evaluated at x equals to xl, right? So you can find fi plus 1, right? How you can find? Now I don't need to write again and again, like I can write fi plus h f dash of xi plus h square by 2 f double prime of xi, so on, right? Similarly, fi minus 1, I can write fi minus h prime h f prime of xi plus h square by 2 f double prime of xi and so on, right? Now observe that here is the double derivative down here. Okay, so what operation shall I do? Okay, what operation shall I do so that I get f double prime of xi easily? Ideas? See, that means I have to eliminate this guy, right? I have to eliminate this guy, and we can easily eliminate this guy. How? Just add these two. If you just add these two, plus h of f prime xi minus h of f prime xi just get cancelled. And then you have the addition of 2 f double prime of xi, right? You understood previously, in order to get the single derivative, we subtracted both of them. Okay. Now, in order to get the double derivative, we are adding them up. So it's up to you what you want. Okay, what you want to do. So what we will do is fi plus 1 plus fi minus 1. That is like if you add the two of the above quantities, what you will get? It is like 2 f of I, right? This term, it cancels. Okay. Then what happens? This term gets added, right? What will it be? S square f double dash of xi, okay, plus order of h cube. Okay. Right. So now can you see that we are so easily we came to this formula? Okay. What you have to do? Divide by h square. Divide by h square, right? Because there is this coefficient here. So like fi plus 1 plus fi minus 1. Yeah. Sorry. Fi plus 1 plus fi minus 1 minus 2 of fi by h square, right? Equals to, so there is some order of h cube term. Can anyone correct me? What will be the term? See, we are dividing by h square. So it will be h, right? So this is just f double dash of x. So you can see, I will write in a proper way. Okay, I will write in a proper way. F double dash of xi is equals to f I plus 1 minus 2 f of I plus f I minus, sorry, I should have written I minus 1 here. I plus 1 by s square, right? By s square plus order of h. Okay? Okay with you? Ah. You see, this is the observation. Okay? So what it should be? H fourth. Yeah? So then what will be here? H. See. Second order method. Okay? And there is a name. There is a name for this formula. What is the name? Since you're using 3 points, you're using fi, you're using fi plus 1. In order to compute the double derivative, hence this is not formula. Okay, you're using 3 points in order to find the double derivative. Hence, this is known as a 3-point formula. Okay. Okay. So you must have observed that the first order scheme, first order like forward difference scheme, is which order accurate? First order scheme like is first order accurate, right? Forward difference and backward difference are first order accurate. Order of H. Now I say that we can make it second order accurate. That means you see, I am even going efficiently. Okay. So now I am asking to myself, like, can I devise a numerical method in order to compute the first derivative, that is f prime of x at x equals to xi, which is second order accurate instead of first order accurate, which was previously. Got it? Okay. So that is the motivation, and we start like some of the calculation for that. So what is our aim? Aim is to devise, okay, to devise a forward difference scheme which is second order accurate. Okay, which is second order accurate. Okay, that means the order term should be like order of h square. We did not have this previously. We have this previously? No, right? Previously we had order of h. If we do square, it will be more efficient, right? Because the error will be less. So therefore, we are devising a new method. That's the motivation. Okay. For that, as usual, we need fi plus 1. Okay, what will be that? You know already. Fi plus h f prime of I plus s square by 2 f double prime of I plus so on. Okay, order of h cube. Okay. Can you give me this formula for this one? Fi plus 2. Fi plus 2 is what? F of xi plus 2h. Is it? See, what is xi plus h? Xi plus 1. And then again add it xi plus 1 plus h. What will be xi plus 2? So instead of writing all the steps, I just wrote xi plus 2h. Okay. So now instead of just h, you will be having 2h everywhere in the above formula. So that means this is fi as usual plus instead of h, you will have 2h because this guy is 2h. Then f prime of I, isn't it? Plus 2h whole squared by 2 fi double prime plus 1. Any issues? Okay. So this method might seem non-trivial, but I'll try to make it as simple as possible. Okay. So our aim, as I told you in the above step, is like to find fi prime so that it is a forward difference scheme. That means it will be written only in terms of the forward points. Only in terms of the forward points. None of that means there should be some a fi, some constant we don't know yet. There will be some b having fi plus 1 because it's a forward method. Okay, there can be also some c fi plus 2, isn't it? We don't know what are these constants yet, but this is by just applying the basic common sense of forward difference scheme that it will have only the forward points. We can write that fi prime is some multiple of fi plus some multiple of fi plus 1 plus some multiple of fi plus 2. Okay, and the numerical method, since it's a numerical method, there will be some error associated with it. Okay, but we don't know yet what's the error. So what we will write, order of say h to the power some p. We don't know p. It will be order of h or h square or some, we don't know yet. So this is the scheme, how it will look, we know. Our job now is to find these constants A, B, and C so that we'll arrive at a formula and make our forward difference scheme more accurate. Okay. Okay. So, yeah. What do you suggest we do next? Fi is Fi, we can't do anything, but we can do B of Fi plus 1. Okay. We have B of Fi plus 1, right? What is Fi plus 1? Yeah, you have that. Do we have info about Fi plus 2? Hmm? That is there, right? So we have it. What is that? It is Fi plus h of Fi prime plus h square by 2 Fi double prime, so on. Okay, plus C Fi plus 2, that is Fi plus 2h Fi prime plus so on. Okay, isn't it? Yeah, got it, right? Okay, so like just eyeball that equation. I can write this. Can I write this? Everyone okay with this? See, AFI, then BFI I am taking, CFI I am taking. All those. Okay. Can I gather similarly Fi prime terms? What will be those Fi prime terms? Hmm? B plus, B plus, try to eyeball. Okay. You can do in your notebook, but I suggest you try to eyeball. Your brain will work. Okay. Okay. Is it okay? Yeah. Okay. So is it okay? Similarly, is it okay? Write this h square term here. So that you can club them together. Okay. Similarly, like these terms, like you can try it out on yourself, like by yourself, f plus like b plus 8c h cube by 3 factorial, that is 6 fi triple prime. Okay. Plus there will be something else also. Okay. Is it okay with you? You might not get this because I have not written explicitly what are these h cube terms and all, but you can do it. Okay. So, yeah. Suggest me like what I should do next. See, I won't. So we have written Fi prime in terms of Fi prime. Okay. If this guy, Fi prime, is written in terms of, it hints us, it cries to us that we should set A plus B plus C equals to 0, isn't it? So that this Fi terms goes to 0. Also want to set the term for Fi double prime to be 0 because Fi prime is here, right? So that means B plus 4C times h square by 2 equals to 0. But we want this guy, Fi prime. So, but we have a coefficient here, B plus 2CH. So we have three equations: a plus b plus c equals to 0, first equation; b plus 4c times h square by 2 equals to 0, the second equation; and the third equation is b plus 2c times h equals to 1. H is given to us. You don't need to worry about it as an unknown. H we already fixed. So all the unknown quantities are a, b, and c. Okay. Since we are given three equations and we have three unknowns, that means we can find a, b, and c. Find a, b, c. Okay. So, like, can you observe something here? Like, as she noted down the values, I can write prime equals to now minus 3fi. Just check if it is okay, correct. Hmm? All right. So, like as you can see, fi prime equals to minus 3fi plus 4fi plus 1 minus fi plus 2 by 2h plus order of h square. We have two important points to make here. One is it uses three forward points: I plus 1, I plus 2. Therefore, it is a forward difference scheme. Okay. Previously, for a forward difference scheme, we only had order of h. We only had order of h. Now we are having order of h square. So you can see this forward difference scheme is more efficient as compared to fi plus 1 minus fi by h. Isn't it? Where you had order of h. Here you have a different formula and an order of. Another important thing I want to point out. Just add the coefficients together. Minus 3 plus 4 minus 1. What you get? 0. So something is there, something is happening. Okay. It's not just popping out like this. So there is something interesting in this such that the coefficients are adding to 0. So that's how beautiful the math is. Okay, it will always spit out the true things. Okay. Yeah. So similarly, you can get a backward scheme also. Okay, now like why we can have only forward scheme, we can have also the backward scheme. So I won't go into details, but I'll just write the formula for the backward scheme. Okay, for the backward scheme, backward difference, which is second order accurate. Okay, we know the backward scheme with first order accuracy. Now I'm talking about backward difference with second order accuracy. I'll just write the formula here. But we will proceed in the same way as we had last time. Okay. So yeah. So you can see like the difference. I am taking now the backward points I minus 1, I minus 2. Previously you had taken I plus 1, I plus 2. That's the forward. Now it's the backward scheme but order of h square. Okay, similarly you can develop the central difference scheme also. Similarly, like using this idea of 3-point rule and making like now you know how to create a forward difference scheme with a desired accuracy. Here p equals to 2. We got p equals to 2, order of h to the power p equals to 2, order of h square. Similarly, you can find double derivative also using this kind of schemes. Okay, any derivative you want, you can calculate. I have written it here. I will not write in this lecture. You can refer to my notes. Okay. So like we'll just have a brief outline. Like many lectures, many courses, they teach you only about uniform grids. Okay, but in real life scenarios, when you consider real world problems, your grid is not uniform. Taking the uniform grid means like you are taking a very simple case. Okay, sometimes your grid might not be uniform, might not be uniform. For that, like uh, uh, we can discuss something like how to compute the derivatives if the grid is not uniform. Okay, how to compute derivatives, and just by using bit of like common intuition, you can argue a fact that okay, it is okay to take the grid to be non-uniform, but how, like there should be a pattern in taking the grid to be non-uniform. Okay, that we will see, that will derive. Okay, that will be the last part of today's. So we'll talk about the non-uniform grids. Okay, so non-uniform grids means non-uniform grid means okay, then you have xi minus 1. Okay, that means xi minus xi minus 1 is not equal to xi plus 1 minus xi. Is it okay? Then it is non-uniform, right? Okay. So basically, I would like to introduce a notation here. Okay, just to avoid confusion, I would like to introduce a notation. What is the notation? Whatever I have written it here is like delta x I minus 1. Okay, that's the notation. Whatever I have written here is delta xi. Is it okay with you? It's just the notation I am defining. Okay. So now you will see that the definitions are very similar to what you have already had, but there will be just these terms delta xi minus 1, delta xi instead of just h. So write it down like if you have fi prime as before, minus fi as before, but now you will have delta xi plus order of delta xi, and this will be the forward difference scheme, right? You know why it is forward difference. You know what is forward difference. I am taking I plus 1. Now similarly you can write fi prime equals to fi minus 1 by delta xi. Yeah. Yes. Is it okay? Yeah. It's okay. So you need to have delta xi minus 1. Okay. That's how it is different. So you're taking the backward point I minus 1. Then it will be order of delta xi, right? Minus. So it is backward scheme. Okay. So this is how like when your grid is non-uniform, things are getting different now. So similarly, we can attack for like central difference, but we don't know how to. Okay, therefore we'll try to derive it. Okay, central difference. Maybe you can write fi plus 1. Okay, so just help me out. Like fi plus 1, then what should I should write? Delta xi, right? Isn't it? Fi prime. Okay. Okay, so let me write again. Delta xi times fi prime, isn't it? Plus delta xi square by 2 fi double prime and so on, isn't it? Now we know from our central difference scheme which points were used, I plus 1 and I minus 1. Is it correct? So we have to write fi minus 1 as well, right? So how will we write fi minus 1? It will be fi minus delta Yeah, is it correct? Hmm? Yeah. So I have to be very careful while evaluating these, like when to use which step size. Okay, you have to be careful. So similarly, you can do like delta xi minus 1 squared by 2 fi double prime, right? Plus 1. Is it correct? It should be minus, right? So these are small, small, tiny things where you're you need to use a bit of brain. Okay. Okay. So what should I do next? Hmm? Add. Yes. So he has gotten the idea a bit. Okay. So now we need to subtract. So depends addition subtraction depends on what we want to find. If you want to find the single derivative fi prime, we need to subtract, because if you add, this term will just vanish. Therefore, if you need also like the second derivative, you need to add, because then fi double prime will prevail, right? So you need to subtract and add depending on the thing you need. We for now we need first order derivative. So we need to subtract, right? So what should I subtract? Fi plus 1 minus fi minus 1. What should I get? Anyone? So fi will cancel out, right? So you'll get delta xi plus delta xi minus 1 times hmm? Hmm? Mm, it's just simple. Delta xi square minus delta xi minus 1 squared by 2 times fi double prime plus 1, right? Then what shall we do next? It's the same thing as we have been doing. It's the same thing. Hmm? Uh, tell. Loud voice. Yeah, here you can't take it to be 1. Okay, here it is not like, here we have, so here we can't vary delta xi minus 1. It's up to us. It's given to us. So you can't set delta xi plus delta xi minus 1 equal to 1 as previously, because there you had A, B, C as variables that are arbitrary. Okay, then we had certain equations to be fulfilled and we found the ABC. Here delta xi and delta xi minus 1 are the step size, and we already had like those step sizes given to us beforehand. Okay, so is it correct to write this fi prime? You can divide just by delta xi plus delta xi minus 1, which is the coefficient of fi prime, right? Then it will give you what is fi prime. Simple, right? So what is there? What will happen? Like fi plus 1 minus fi minus 1 by, yeah, plus plus c plus, you can attack it. See, the order term on the right side here, it is like b square minus a square. So it can be written as b plus a into b minus a. Okay, isn't it? Yeah, b plus a into b minus a. But b plus a is, so when you divide, what will prevail? B minus a. Because b plus a, numerator denominator cancels. So b minus a prevails. What is b minus a? Hmm? Is it correct? So then you will have a bit of complicated terms. Okay. Now, now here comes a few, like we can uh, take some ideas from here, like how non-uniform our grid will be. You can't take any non-uniform grid. Okay, here it will help us in predicting how non-uniform the grid is. Okay, so here I have written some points. So depending on the nature of the grid, one higher order might dominate another higher order. Okay, so suppose you have like delta xi is very close to delta xi minus 1. If delta xi will be approximately equal to delta xi minus 1, it's not exactly equal, it's approximately equal. Maybe one grid size here on the right you will have 2.1, left you might have 1.9. So almost they're equal, but they're different, non-uniform still. So if you have this guy, then what will happen? Can you say what will happen? See, whatever we are doing, we are applying each step our basic intuition and common sense. Nothing heavy math we are applying. See, when delta xi is delta xi minus 1, see this higher order term. Order of delta xi minus 0. So that means who will conquer? Who will conquer? It will be the next term here. We don't know the next term. So we have to find that term. Okay. So I will just write it for you. It will be like just try like you can take this third order also. Okay, if you want, but you can find this term as delta. All are square terms, mostly square terms, and you can see like a square plus b square minus ab is there. Okay, this is just algebra you need to do, just minimal algebra. But now you can see if delta xi is very close to delta xi minus 1, this guy, that implies delta xi minus delta xi minus 1 will be very close to 0. Okay, then that implies our higher order term depends on these guys, delta xi square plus delta xi minus 1 square minus delta xi minus 1, right? How this guy looks, how this expression looks, it will be like, yeah, it will be like maybe 2 delta squared minus delta xi squared, right? It will look like that because delta xi is approximately delta xi minus 1. So it will look like delta xi squared. Okay, or even delta xi minus 1 squared. It doesn't matter because delta xi is approximately delta xi minus 1. It will be of the same order type. Okay, so that means order of this squared is there. That means second order accurate scheme. Okay, so if you have a non-uniform grid, you don't have uniform grid, you have a non-uniform grid, still, if you have additional condition that delta xi is very close to delta xi minus 1, then you have a second order method. Okay, okay. Now suppose the next case, delta xi is very like larger than delta xi minus 1. If it is much larger than xi minus 1, then what will happen? Or even delta xi is very smaller than delta xi minus 1. Then what will happen? Any ideas? Okay, so it is a task for you. Which order accurate it is? Okay, so it will be first order accurate. Okay, so you now know like so if you have a so like if you have a non-uniform grid, Okay, if you have a non-uniform grid and you want to have high accuracy, then you have only one choice. Here I have covered all the choices. Either the previous grid size might be comparable to the next grid size, or grid size will be very less than the other grid size, or it can be larger than the grid size. We have now. I have taken the last two possibilities here, and your task is to show that it is indeed first order accurate. But when you take delta xi, almost approximately equal to delta xi minus 1, your scheme will be second order accurate. So out of this, which one you should choose? So you have a non-uniform grid that you, but in order to have the non-uniform grid, you can't compromise with the accuracy. And so in order to take the accuracy into picture, which type of grid, non-uniform grid you should take? Which type of non-uniform grid you should take? First order or second order?